Okay, so a very good evening to everyone. I am Shohardo Ghosh. This is all my introduction being given in the first page of this course. So, as you already know, the course is already over, but then as per our PMRF norms, this is an extra revision session that I am conducting. This will be for a shorter period, it will be only 1 hour session where I will be going back through all the notes that have been covered in the previous sessions. So basically, these were some brief introduction regarding the importance of the course of signals and systems. So I hope now you are well aware of the importance of this course, and not only that, I will be taking future courses and various topics such as analog circuits, digital circuits, control systems, communication system, DSP. So now you are in a well versed and suitable position for being able to tackle these courses. Okay, so initially in this course we had the simple mathematical preliminaries where we learnt about basic calculus, the limits and derivatives, integrals, and the trigonometric and hyperbolic functions. So as I was emphasizing that time that okay, so this c to the power jx is cosine kx plus j sine x. Okay, let me try to use the what yeah. So yeah, so let me try to use the laser pen so that I'll be just highlighting everything over here. I will not be writing anything new, and I hope that all of you have been given access to the link which has all the recordings. So let me open that link for you. So it's yeah. Okay, so I accidentally went on to a different link. So let me share that link to you. Alright, so the link has been shared in the Google Classroom and this Google Meet. Okay, so e to the power jx is cosine x plus j sine x. This is the Euler's identity, and you should be using this whenever you are asked such questions regarding the hyperbolic functions. So for example, cosine x is half e to the power jx plus e to the power minus jx. Then the sine x equals to, okay, so alright, yeah, it's clear now. So fine. Alright, so here to find the value of j sine hyperbolic x. So the important property to be used over here is the Euler's identity, e to the power jx equals to cosine x plus j sine x, right? This is an important formula. Then how do you manipulate these formulae for for cosine x and sine x? If you remember these fundamental properties, then if you are given anything to be manipulated, such as cosine hyperbolic of jx, so cosine hyperbolic jx or something like that, you can be using either these properties. So cos hyperbolic x is e to the power x plus e to the power minus x by 2. Sine hyperbolic x is e to the power x minus e to the power minus x upon 2. This is cosine hyperbolic jx, and basically this is cosine of x, and same goes for sine hyperbolic of jx. So once you know each of these important individual formulas, you will be able to solve anything and everything. same goes with this one. Okay, so you also need to revise some of the concepts related to these standard signals. The first standard signal that we learned in this course is the direct delta function. So direct delta function actually can be modeled in a variety of ways. You can show it as a rectangle with an infinitesimally small width and height, and group becoming infinitely large. That's one way. So another way could also be the triangular pulse. So the width of this pulse, triangular pulse, keeps on decreasing and the height keeps on going up. You can also represent the pulse in the form of a Gaussian, where the standard deviation is almost a measure of the width and this is the measure of the height. So as your sigma or the standard deviation goes down, the height, which basically is 1 upon root over 2 pi sigma square, starts becoming infinitesimally large. So such cases can be looked upon. So basically, but for this sake of this course and the simplicity, just assume the simple rectangular pulse. So this is the scaling property of the impulse response, impulse function, and certain properties that should be remembered. Delta t is 0 when t is not equal to 0, and it's not equal to 0 when t is equal to 0. That means it jumps to infinity, and the integral under this is always 1. And then when you scale the integral value by a, then a comes out and you actually get this. So there has been a lot of discussion regarding this. Okay, then you have another important function, which is the unit step function u of t. U of t is actually equal to 0 for t less than 0, and it is equal to 1 for t greater than 0. Okay, and then if you look at very carefully, unit step is actually the time integral of the impulse function. Okay, and there's another function. If first you had the impulse, then you had step, and now you have ramp. So I'm increasing the order of complexity or the order of the polynomials involved. So ramp, there's something r of t, it's equal to t for t greater than 0, it's equal to 0 for t less than 0. And if you look very carefully, ramp is the time integral of the unit step function. Okay, all right. Okay, then you have cosine x. Okay, fine. So you also have types of signals where you have odd signals, even signals. Okay, so odd signals are those which are antisymmetric about the origin. Okay, so whatever happens goes up over there, in the same distance from the origin it goes down. And for even signal, that's a mirror, it's almost a mirror image around the horizontal the vertical axis. And then this is very simple. Second, finding second order derivatives, you have already learned this in your 10+2, so I don't have to repeat this over here, and it's also a part of your basic revision of your first year calculus. I mean, it's not even first year calculus, it's class 11. Okay, then a small revision of these trigonometric identities. 2 sine a cos b equals sine a plus b. Please go to the entire chart if you have them. Okay, and then you have things like sine x plus sine y equals to sine of a plus 2 sine of a plus b upon 2 times cos of a minus b upon 2, something like these charts are also available, like when you add the sine, when you add a sine, cosine. Okay, even these are important. Then this is revision of systems, basic systems, capacitors, parallels, what happens when they're in parallel. Okay, so this was actually if you see, this was actually a derivation of how the parallel expression comes out. So in exams you don't need to derive that, obviously, but then you know that for the interviews. Yes, Then you have the limits. This is you have to, there are various ways of solving limits. You can use the concept of rationalization, where you make the where you try to remove all the square roots and you bring out things from the 0 upon 0 form. Okay. And you can also use the L'Hospital's rule. If things are of the form 0 by 0 and infinity by infinity, then you take derivatives of both numerator and denominator and try applying that. Okay. Another important thing is the Taylor series and the Maclaurin series, where you try to express any nonlinear function as a function of various or polynomials, a constant, a first order polynomial, a second order polynomial, third order polynomial. So you sum up all of them very carefully and you will get the original function. You have to reconstruct the function back. This is almost analogous. Now that you know signals and systems and Fourier transforms in great detail, you can say that it's kind of a basis expansion. Just like Fourier transform and Fourier series, we write things in terms of summations of um, these sines and cosines of multitude of harmonics. Similarly, here Taylor series uses the polynomials as the basis functions. There we used to have each of these sine, cosine waves of varying frequencies as basis functions in the Fourier series, and in the Taylor series we have the um, each of these polynomials: first order, second order, third order, fourth order, fifth order, okay, so on and so forth. That's the Taylor series, different basis functions. Real life non-linear systems. What happens when a system is non-linear? Change in input delta v by delta I is not same throughout. Okay, so I had explained the small signal model over here and the importance of this Taylor series. The importance of Taylor series, you will I guess if you have done any devices course or analog circuits course, you must have gone through this by now, or you may be going through that in your future courses. Okay, that's week one in a great in a greatly summarized manner. Now week 2, so we had continuous and discrete time signals. I think I shouldn't be editing them anymore. Okay, continuous and discrete time systems. Then you had even and odd. Continuous means that the time axis can take, you can take any value at any point of time, there's no difference. Okay, and then discrete time, the time is indexed at integers 0, 1, 2 and so on. Okay, and you have values only at these indexes and nowhere else. Okay, so you don't have the entire signal, you just have a finite set of, or even if it's infinite set of collections but at finite indices. Then you have even and odd signals that I mentioned earlier. This is an even signal, then this is an odd signal. Okay, periodic signals. So what is the condition for periodicity? If you have a signal xt and it's equal to x of t minus capital T, and this holds for the entire interval, it's not just for a small location that you see, it has to repeat throughout the time. So in reality, in real life, no signal is completely periodic. And what is the reason? The reason is that you never have things being switched on. For example, you are generating a sine wave in the oscilloscope, you are generating a sine wave from the function generator, signal generator, but then the signal generator was not on from the beginning of eternity. The signal generator was manufactured at some point of time, and after a certain point of time you switched on that signal generator and let the time be 0. So after that, let's suppose you kept this on, so it remains oscillating forever towards the right, but in left there's nothing over here. So in real life, periodic signals do not exist theoretically, in a theoretical sense, in the real life. But for if you practically may look at things, we try to see things in finite duration of time, and from that perspective, for the entire duration, when you look from 0 to some time t, sometime big time t naught, t naught is very large, and in that interval if things satisfy that x of t equal to x of t plus tau, we call that the signal is periodic in the real life sense. Okay, so this was an example of sin t to t, how to determine the period. So when you have multiple signals x1 t, x2 t, xn t, each of them with different time periods, how do you determine the period of the signal? And before that, the more fundamental question to think about is whether the signal is periodic at all or not. So we try to check the ratios of all the time intervals, time periods, t1 by t2, t1 by t3, so on till tn minus 1 upon tn. Okay, all these ratios are checked, and if all of these ratios turn out to be rational number, then we are sure that this will be a periodic signal. If at least one of these ratios turn out to be any rational number, let's say root 2 or pi or something, or some power of e or anything that's not rational. I know you sure you know rational number means p by, it's something on the ratio of p by q, where both p and q are integers and q cannot be 0 obviously. So these are rational numbers, and if these turn out to be fractions, it will be more clear, simple, then it's periodic. And what is the period? The period is the lowest common multiple of all the time periods of the individual signals. You have t1, t2, tn, so you take them all and see their LCM, that's the overall time period. Okay, fine. So let's see, for example, I took this sin t, sin 2t, I wrote it as a sum of two separate periodic signals, and then you see 2 pi and 2 pi upon 3, their ratio is a rational number, so it's periodic signal. It's evident over here. The LCM is 2 pi. Okay, so this is scaling, that's it, scaling of signals. So okay, so when you have a signal, let's say x of t from minus 1 to 1, okay, so you can, when you scale it by x of a t, what happens is that the limits change from minus 1 upon a to 1 upon a. If a is greater than 1, then that means the signal is compressed, that means the size becomes small, and if a is less than 1, then it's called expansion. Okay, now this is the period of a discrete time signal. So for a discrete time signal, we need to ensure that omega naught has to be a rational multiple of pi, something like 4 by 7 pi, 3 by 13 pi, something of that kind. Pi has to be there and a rational number has to be there, only then will you be able to find the period. Okay, so I was mentioning over here maybe about how you generate or store samples in a computer. Varied rational multiple of pi, and once you find that, then find n equal to 2 pi upon omega naught and see the nearest integer to this. It's not the nearest integer, but then yeah, you try to multiply it by some sort of a number which gives you an integer. Okay, so you see I've explained the concept of signal scaling along time axis. You have signal xt, you have this at, the a is the scaling factor. A is greater than 1 implies that the signal is being compressed, a less than 1 implies that the signal is getting expanded, as I explained earlier as well. Okay, this is simple. Delay, this is signal xt, I delay it by tau, so it is a delay means a right shift, and if you want to advance, it gives x of t plus tau, it moves left. A left shift implies an advancement in time, a right shift implies a delay in time. Okay, I also gave you a method to check how to write the expression for signals transformation. So you have this signal, this one changes, so you try to write a mapping between this and this and this and this. There will be a linear equation, and you write this time axis in terms of this one. Okay, so tabulate all the critical points for xt belonging to t. By critical points, I mean those points when the starting and the ending. Okay, any of these points, I mean you need at least 2 points and that's it. And then you find the relationship between the two and replace x of t, x of az plus t, and so on. And note that for discrete time signals there's something important to be noted, that that the entire thing inside this bracket has to be an integer finally. If you see something that it turns out to be not an integer, so let's say you have x of 3 by 2 where x is said to be a discrete time signal, and then that value will actually be 0 because the signal does not take any meaning in that. Even signals, odd signals, then neither even neither odd. So you can actually decompose signals as sum of even and odd signal. So if you have a signal x of t and you have been asked to find the even and odd part of this signal, you take x of t and you take x of minus t. You take the average of them, that's the even part. And you have xt and you take a difference divided by 2, you get the odd part. Very simple. This was an example of finding out the even and odd part of a signal. Then orthogonality of signals. So if you have two vectors in general and their dot product in various senses, the integral from minus infinity to infinity, integral of the product of the two signals, or let's say the summation of the x1n, x2n, n equals to minus infinity to infinity, that is 0. Then what happens? That becomes the dot product. Now if the dot product of two signals is 0, that means that the signals are orthogonal. Okay, that was week 2. Now let's go to week 3. We had covered a lot of things. Okay, so now in week 3 we studied about the frequency domain representation, basically the I shouldn't be doing this, Fourier transform. Okay, Fourier transform. So basically we had the definition of Fourier transform, Dirichlet condition, inverse Fourier transform, and frequency time uncertainty. So you have a signal xt, its corresponding Fourier transform is x of omega. How do we find x of omega? Is the integral of x of t and the basis functions in basis functions, I mean the set of functions which are used to construct the signal is considered to be the complex exponential signals e to the power minus j omega t. So based on these complex exponentials you build up a signal. So this is your spectral spectrum of the signal x of omega, and given a spectrum x of omega or the Fourier transform, you can obtain back signal. You see the two relations very similar looking, but the difference is in this. But it's important to understand that not every signal has a valid Fourier transform. So what are the conditions that a signal must satisfy in order to have a valid Fourier transform? So first of all, the signal must be absolutely integrable over time. Okay, like this, absolutely integrable over time. This one is violating this, so this one does not have any Fourier transform. Then signal must have finite number of maxima minima over a given interval. So for example, cos 1 upon t, this has infinite number of maximas and minimas, infinite number of oscillations, very close to 0. So this violates this definition, this Dirichlet condition. So cos 1 upon t does not have any valid Fourier transform. Then you have the last one, which is the signal must have finite number of discontinuities over a given interval. So you see this one, this has infinite number of discontinuities in this small interval, so you cannot build a Fourier transform for this. Then there are standard properties, and these standard properties hold for not just Fourier transform, it's for continuous time Fourier transform, discrete time Fourier transform, continuous time Fourier series, discrete time Fourier series, Laplace transform, as well as Z transform. All these 6 transforms which are a part of the course satisfy almost every property being mentioned, because of the underlying structure of the signals that remain the same throughout. You have ax1t plus bx1t, that translates to the linear combination in the Fourier transforms. Then you have time shifting, becomes a phase shift in the frequency domain. When you have multiply a signal by a sinusoid or an exponential term, then the signal shifts in the frequency range. So it's centered around 0. So once you multiply it by a fixed frequency in complex sinusoid, it shifts around a different carrier frequency. This is called which is called modulation. Determine the magnitude. Okay, so this was a simple question. You have to find the magnitude with this. It's a complex number, so that's 1. Determine this frequency spectrum sin omega naught t. The typical sin omega t signal has two peaks, each corresponding to omega naught and minus omega naught, and a phase term of 1 upon j. So the magnitude actually looks the same. We have a single frequency. Actually, let's look at this only. There's a single frequency component. Cos omega naught t also single frequency component. Then this is a bit small discussion or the starting discussion on the system, where you have a CR circuit. Okay, it's a differentiator circuit. So transfer function is basically the ratio of the the Fourier transform of the output to the Fourier transform of the input. It talks about the response of the signal of the system to various frequencies. For example, if you look at h of j omega rc, okay, so I have done the analysis over here. So I have taken the magnitude over here, omega rc by 1 plus omega rc square. So at omega very low frequencies, h is close to 0. That means it does not allow low frequencies to pass through. At omega tending to infinity, mod h is very close to 1. That is the maximum gain it can provide is 1, because this is not an active circuit. Active circuit can provide you gain greater than 1, but this is not, and this is passive circuit. And this is a bit about the phase. So see that h of j omega, if I plot the transfer function frequency, this is called frequency response. For higher frequencies, this system passes high frequency signals, and this circuit does not pass low frequency signals. So this is called a high pass filter, and these are actually linear time invariant systems. So when you give us input to sinusoid to it of single fixed frequency, you also get the same kind of signal as an output. That means you get the same frequency output, but only thing is that the magnitude and the phase changes, and this magnitude and phase change is a function of the frequency. Okay, so this is the question: why is e to the power minus at Fourier transform not possible? It's obvious, because of the absolute integrability. So this is a critical signal, the pulse signal. So pulse signal has a Fourier transform which looks like sync. So just asking you to revise the notes that have been provided in the NPTEL classroom lectures. So just look at the notes and be aware of the convention used for sync and sampling. Sync and sampling, be careful about the notation given, because these notations vary across courses. These could vary across notes. So if you blindly follow mine, then it would be an issue. So I would request you to have a look at the notes, so that you are in the right track, you get the correct answers. And this is ft equal to, this is decaying exponential. Okay, decaying exponential e to the power minus a t ut. How does the spectrum look like? The spectrum looks like this. This has significant amount of low frequency components, and high frequency components are almost absent. Yes, and some other important signals, the left sided signal over here, the phase, if you see, response will be positive, and this phase response for the causal signal is negative. So such kind of signals which exist for t greater than 0 and don't exist for t less than 0, that means it's 0, these are called causal signals. Signals which are 0 for t greater than 0 and exist for t less than 0, these are called anti-causal. And if things exist in both sides, that's called a non-causal signal. Alright, and non-causal signals have no phase response. Phase response is zero actually, you can't say it does not exist. And then you have another important signal, which is the signum or the sine function. So sine function is 1 when time is greater than 0, sine function is minus 1 when time is less than 0. So its response is 2 upon j omega. That's week 3. Now let's go to week 4. Okay, so week 4 was Fourier transform and some of its properties. Okay, so here we use the some properties when you are breaking signals and trying to construct the Fourier transform of each of them and then add them up based on the linearity property. Here I had taught how to write a given signal in terms of unit step function, and based on that derivative based on the derivative of a function you can write it in terms of impulses, and then it's easy to find the impulse Fourier transform. That's one shifted impulse gives e to the power minus j omega tau, so you can easily find this Fourier transform. And then based on the fact that yt equals to dxt dt, and the corresponding frequency transform has a multiplication by a factor of j omega. Okay, so for n times differentiation you have multiplication of j omega n times. Same thing I have shown for this one as well. This is ramp function, how to construct a signal in terms of ramp, and you differentiate it you get ut, double differentiate you get unit step unit impulse, and then you take its Fourier transform and multiply by j omega square. This one utilizes the concept of modulation and the two-sided exponential signal. So the important thing is that e to the power minus at and such kind of signals Fourier transform are very standard, and you should remember them for the purpose of your exams. Okay, so this is simple modulation. Calculations are a bit involved over here. So now here in week 5 we learned about systems. We learned about systems, linearity and time invariance, LTI system, frequency response, and differential equation based representation. So linearity occurs when you have both superposition and homogeneity. Superposition means that if I have x1t and x2t separately giving outputs y1t and y2t, their summation will give the output as summation of y1 and y2. That's superposition. And homogeneity means that if you scale the input. Yeah, Ankit, do you have any question?
Lagging. I have audio issue. It's missing it sometimes in few seconds.
Okay, fine. Since I'm recording this, you can watch the video later. You can watch the video as well. Okay, so I hope that's not an issue. If you have any doubt, then you can write over here. And if you have any audio issues, then don't worry. Then you can watch the recorded version as well um, in the sheet that has been provided by the NPTEL. So system follows superposition principle. Actually I'm going a bit fast because I have to cover all of them in this short time. And then if you have a linear system that satisfies both, so you have a weighted input combination of x1 and x2, the corresponding output will also be added in the same manner. Okay, so that was linearity. And time invariance means if you shift the signal, if you have a signal xt and its output is yt, then if you shift the signal xt and then pass the shifted input to the system and you get an output, the output will also be the shifted version of the initial one. Okay, that's time invariance. That means that the system does not cause any deviation in the shift. Okay, whatever shift you do in the input, that shift will automatically be visible in the output of the shifted input. Okay, time invariance. And now an important trick that I mentioned for time invariance was that you have to see whether things like this, whether the time variable is being manipulated or not. Like f of 2t, f of sine t, f of t square plus 3, these are time variant systems. Things like f of t plus minus k, these are not time invariant, these are not time variant, these are time invariant. Then LTI system, LTI system's fundamental property is the property convolution, which is this expression, the convolution integral. And the eigen function of a LTI system is the exponential e to the power j omega t. So if you put this out, then you will get another exponential with shifted phase and gain term. And then every LTI system, you can, based on the impulse response, you can write the frequency response h of j omega. So CR circuit, we had already calculated its frequency response. And now you can see the shortcuts. Capacitor at 0 frequency becomes open circuit, and high frequency it becomes short circuit, and the opposite holds for inductor. So you can be using these techniques to find out whether a circuit behaves like a low pass filter or a high pass filter at different frequencies. Okay, this is the phenomenon of resonance. So these are the linear constant coefficient difference equations. You will be given this kind of a system relationship in terms of differential equations, and then you need to use the differentiation property of the Fourier transform, and then you will be able to write the h of omega, the transfer function. Okay, let's go to week 6. Week 6 we had the same things, convolution integral. Okay, I shouldn't be using this. Convolution integral was there, more detail. And LTI system properties: cumulative, commutative, distributive, associative, memoryless. Okay, let's look at it. Convolution integral. Okay, this is derivation, so you can ignore this. Okay, so I had shown how the convolution integral actually takes place by sliding this rectangle throughout the signal space. So this was the convolution of two rectangles. So this was the associative property. A plus b plus c is a plus b plus c. That's very simple. It's simple algebra. And LTI systems show this commutative and associative property. This is distributive property. Nothing much to discuss over here. Memory means that this yt is a function of the present value of t only. It doesn't depend on past values like x of t minus tau log of 1 plus t. These are memory terms. Okay, future or past. These should not be there in memoryless system. Invertibility, that means if you give xt, there exists an inverse system which will give back xt. Causality, so as I mentioned earlier, the impulse response should exist only for t greater than 0. For t less than 0, it should be 0. Causality, the present value of the signal's value should depend only on past and present value of the inputs. It should not depend on the future values. Stability, we discuss in terms of Bibo stability. Boundary input, bounded output. If the signal is input signal is bounded, and correspondingly if the output signal is also bounded, then the signal is stable, system is stable. And that, if you want to verify, you do this by checking the absolute integral of the impulse response. If that is less than infinity, then your system is stable. Week 7. Okay, Fourier transform in complex frequency domain, Laplace transform. So basically, till now we were working on j omega domain, j omega axis. Now we move to sigma plus j omega, a generalized plane. Okay, so there's the Laplace transform. In the Laplace transform, we have an exponential factor, real factor sigma. So e to the power sigma, which determines whether my signal is diverging or converging with time, and the j omega, the imaginary part, which says the oscillations. If omega is small, then my oscillations are slow. Omega is large, my oscillations are fast. So it's a more general way of analyzing the systems and signals. So these are some views of how signals can be and their corresponding locations. So left sided, in the left side of the S plane, signals are attenuated or stable. Right side, these are diverging and unstable. Here imaginary axis, the position determines the frequency of oscillation. Laplace transform, okay, this is e to the power minus st is your basis function, okay, and a general transfer function in a Laplace transform looks in this form. It is ratio of polynomial of s and is ratio of polynomials of s. The roots of the numerator are called zeros and the roots of the denominator are called poles, okay. So for any signal system, if you have um, Laplace transform, you along with that you have something called region of convergence. It is the values of s, the s for which the signal or the system converges or remains stable, like e to the power minus at ut. This one has a ROC that is right sided, and right sided actually means causal because it's right sided, and since the j omega axis is included, that means the system or signal is stable, okay. See, this is the opposite case, same signal, it gives the same Laplace transform, but the ROC is left sided. Left sided means the signal is anti-causal, and because it does not include the j omega axis, it is unstable. Similarly, you can find the ROC for other signals depending on their behavior. So you need to actually expand this xt e to the power minus st and see the values of sigma for which the integral converges, and that is your ROC. And for any given LTI system, if you have n poles, then you have n plus 1 ROCs. See, you have 3 poles, you have 4 ROCs. And very important point, ROCs can never contain any pole, they can only contain zeros. So left sided means anti-causal, right sided means causal, finite strip means non-causal. And for stability, j omega axis has to be included in the ROC. So these are just extension problems of those concepts only. Week 7. Week 8. Week 8 is just repetition of the linearity, causality, shifting, scaling, okay, and derivative. So this is the ROC thing that I have mentioned earlier. So x of t minus tau gives e to the power minus xt x of s kind of a Laplace transform. And okay, so when you have scaling by a in the time axis, then in frequency domain on the Laplace domain you have 1 upon a magnitude scaling and a frequency scaling in 1 upon a. So it means that if you are scaling compressing in time, or if you are expanding in the time domain, you are compressing in the frequency domain, and that is actually the time frequency uncertainty relation. So you have extensions of all the properties in the Fourier transform in the Laplace transform. So I'm not repeating that. Convolution in time domain becomes frequency multiplication in frequency domain. Just repetition of the causality and stuff like that. Week 9. Fourier transform periodic signals, Fourier continuous time representation. It's all the same. Now you are omega t st, all of that we have learned. Now we are moving to continuous time signals. So in that case, what do? We have the fixed set of frequencies. We use the complex exponential Fourier series, and the spectrum looks something like this, the discrete set of frequencies. We also have the corresponding trigonometric Fourier series where you can write in terms of cosine and sine terms, and these are how you evaluate the cosine and sine magnitude components. Okay, and given a signal, you can always obtain its Fourier coefficients very easily. And you can also plot the magnitude and phase spectrum. So for a given signal, periodic signal xt, you can always obtain its ck, general Fourier expression coefficients. So basically this is the actually CTFT of the original pulse, and the DF and the continuous time frequency spectrum is actually the sampled version of the CTFT. So I hope you can revise the set of properties of the Fourier transforms and Fourier series, all the expansion, scaling, and all these properties, just completely repetitive. Then very important is the Parseval's theorem. I would ask you to revise Parseval's theorem in the continuous time domain, frequency domain for all the possible transforms. Okay, especially the continuous time Fourier transform and the discrete time Fourier transform, and the Fourier series. Okay, discrete time and continuous time Fourier series. In these four cases, the Parseval's theorem will be valid. Then, okay, just looked at week 9. Week 10. Week 10 was again discrete time convolution. Okay, so everything is back to the same page. Oh, okay, so this Dirac delta function and Kronecker delta function for discrete and continuous time, and then the important property or theorem is the Nyquist sampling rate. So Nyquist sampling rate states that the minimum sampling rate minimum sampling rate must be at least greater than or equal to twice the bandwidth. And how do we do that? We observe the spectrum, the sample signal, and see the condition where this does not overlap. And if it overlaps, then something wrong happens, and this wrong is called aliasing. And in order to extract back the original signal from the sample signal, use a low pass filter. And these are simply some practice solving of the concepts. Okay, and if you have two signals xt, they're convolved, let's say the bandwidth is 2b, then signal will be multiplying. Okay, will be multiplying the corresponding frequency transforms. So its Nyquist rate will be 2bw, and if it's been convolution, if it is a multiplication, then its signal will have convolution, and that will cause the bandwidth to increase to minus 2bw, and Nyquist rate will become 4 times the bandwidth. This is how the discrete time convolution looks like. This is the differential equation form, and for discrete systems you have the difference equation. Okay, so it's in terms of the difference in intervals of time, discrete indexes, past values of output and past values of input, and based on that you can have two types of impulse response: finite impulse response, where only a finite set of non-zero values exist, and infinite impulse response, where infinite non-zero values exist. And this was the special technique that I had mentioned for doing the normal discrete time convolution. Week 11. So in week 11 we had covered Fourier transform of sample signals, DTFT. So there's DTFT. So you have a discrete time signal, it's not periodic, it's aperiodic. So you have a continuous discrete time Fourier transform. This is continuous, but it's periodic with a period pi. Okay, and that's the only property, and because the rest of them, periodicity, linearity, and all of these are completely same as the normal Fourier transforms. And finally, week 12 that we did yesterday is the Z transform. Same analogy as the S transform, and nothing much to repeat. And only in this case the different thing is the ROC. The ROCs in this case, rather than them being the Laplace transform based Laplace transform based strips, you'll have circles. So if it's causal, it moves radially outward. If it's anti-causal, it converges towards the origin. And if it's non-causal, then it will be a strip or annular ring kind of structure. Stability, for stability, it must include the mod z equal to 1 axis, just like we had the j omega axis for the Laplace transform. So these were some examples that we saw yesterday, and this is a to the power n. Un is an important signal in its corresponding z transform. So that's it for the entire course. I hope you enjoyed and this helped this guys everyone a lot. So good luck and best of luck for exams. Thank you.